Hey everyone, welcome to today's Explainer. I am so thrilled you're tuning in because today we are going to completely demystify exactly how concrete beams are designed. If you've ever looked up at a massive concrete structure and wondered how engineers absolutely guarantee it won't come crashing down, well, you are in the right place. We are going to break down the complex mechanics behind concrete beam design using calcbook software, all while adhering strictly to the rigorous ACI 318-19 standards. We're going to keep this incredibly clear, highly structured, and, honestly, pretty fascinating.
So, to the naked eye, concrete looks pretty much indestructible, right? It's heavy, it's rigid, it's permanent. But the reality is that beneath the surface of literally every solid concrete beam, a hidden, constant battle of forces is taking place. While it looks like it's just sitting there peacefully, internally, the material is fighting off two primary structural villains. And as engineers, we have to carefully, deliberately design against these forces if we want our structures to actually survive.
To defeat those structural villains, here is our roadmap for today. First, flexure and shear basics. Second, the beam design challenge. Third, testing flexural capacity. And finally, checking final shear strength.
Okay, let's dive right into Section 1, Flexure and Shear Basics. Before we start running any numbers in our software, we have to understand the fundamental physics of the two major forces we're battling here. It's actually really fascinating to contrast these two completely distinct types of failure. Flexure is essentially bending. Imagine pushing down hard on the middle of a beam. The beam wants to smile. The top gets squeezed together into compression, and the bottom is pulled apart into tension. Shear, on the other hand, acts way more like a slicing motion. It doesn't want to bend the beam. It wants to physically cut it. This slicing force causes aggressive 45-degree diagonal cracking, usually concentrated right near the continuous supports that are holding the beam up.
Now, to properly design for flexure without things devolving into total chaos, we gotta establish the rules of the game. The American Concrete Institute, or ACI, gives us 3 standard academic assumptions to model our beam's behavior. First, plane sections remain plane, meaning the cross-section of the beam stays flat and doesn't magically warp as it bends. Second, we assume equal strain between the steel reinforcement and the concrete. Basically, they stretch and compress perfectly together as a unified team. And third, our internal stresses are computed using standard stress-strain curves. These rules are what allow us to turn unpredictable real-world physics into highly reliable mathematical models. With the rules locked in, we need to map out our territory. This is essentially the alphabet soup of beam geometry. H is the total overall height of the beam, and B is the total width. Now, D is absolutely critical. That's the depth from the top compressive edge down to the exact center of our steel reinforcement. Finally, C is the depth to the neutral axis, which is that magical horizontal line inside the beam where there is exactly zero stress, no compression, and no tension. Understanding these dimensions is a big deal because they dictate exactly where our internal forces act. All right, moving on to Section 2, the Beam Design Challenge.
Pure theory only gets us so far, so let's transition into building a highly specific real-world beam. I want you to really visualize this as I read off the specs. We are engineering a rectangular section with a 24-inch depth and a 12-inch width. To protect our internal steel from rust and fire, we're wrapping it in 2 inches of clear concrete cover on all sides. Inside, running along the bottom to fight our first villain, flexure, we're throwing in 3 thick #7 steel bars. And to fight our second villain, that slicing shear force, we are wrapping the core in #4 steel stirrups, spaced out perfectly every 12 inches on center. Of course, dimensions are just empty space until we actually fill them with specific materials. These are the heavy hitters, the fundamental defensive building blocks we'll be plugging into our calcbook software. Our concrete is normal weight, weighing 150 pounds per cubic foot, with a solid compressive strength of 4,000 pounds per square inch, or PSI. Our steel reinforcement is tough, rocking a yield strength of 60 kips per square inch, or KSI. And the stiffness of that steel, its modulus of elasticity, is locked in at 29,000 KSI. Now, calcbook software gives us a beautifully logical workflow. Instead of getting bogged down in manual calculations, we just step through the process. Step 1, we simply select our rectangular section and our single bottom reinforcement layer. Step 2, we enter those exact dimensions and clear cover specs we just reviewed. Step 3, we drop in our material properties. And finally, Step 4, we apply the external forces, the heavy loads that are actively trying to destroy our beam. So let's talk about those loads. Our beam spans a length of 20 feet, and it's carrying some pretty serious burdens. We have a concentrated point load of 3 kips. That's 3,000 pounds striking exactly at the 3.5-foot mark. There's another 5 kip point load out at the 13-foot mark. On top of all that, an ongoing uniform live load of 1.5 kips is pushing down on every single foot of the beam. Finally, we apply a standard safety multiplier, a load combination of 1.2 times the dead load plus 1.6 times the live load. This specific load profile is going to generate all the flexure and shear demands we have to resist. Now, here's where things get interesting. A rigorous design analysis obviously requires us to verify the beam's capacity right at the 3.5-foot mark, where that first heavy point load strikes. But when setting up the software, an engineer makes a highly specific, seemingly bizarre choice. They choose to analyze the beam at exactly 3.49 feet. Why on earth would you stop just a tiny fraction of an inch short of the 3.5-foot target? Well, here is a fantastic little insider engineering trick. When you look at a shear force diagram around a heavy point load, the slicing force builds up to a massive peak right before the load, and then it drops off sharply immediately after it. By stepping just a hair to the left at exactly 3.49 feet, we purposefully capture that much larger, much more dangerous peak shear value right before the drop. The bending moment hardly changes at all over that tiny fraction of an inch, but catching that maximum shear demand is absolutely critical for designing a genuinely safe structure. Let's jump into Section 3, Testing Flexural Capacity. We have our beam, our materials, and our maximum loads perfectly calculated. It's time for the big test. Once we feed everything into CalcBook, the software runs all the complex strain diagrams seamlessly in the background. It figures out A, our concrete compressive block depth, and applies standard coefficients like beta 1. Most importantly, it applies a safety phi factor of 0.9. After all the math settles, the software outputs our final flexure defense metric. Our beam has a positive flexural capacity of 160 kip feet. That is the maximum bending force this beam can handle before it fails. But listen, 160 kip feet is literally just a number, until we compare it to what the beam is actually experiencing out in the real world. And this brings us to arguably the most important metric in structural design, the demand capacity ratio, or DCR. It's a very simple question. Are we demanding more from the beam than it has the capacity to handle? Think of it exactly like a budget. If your DCR hits 1.0, you are totally maxing out your credit card. A truly safe, compliant design absolutely must stay under a DCR of 1.0. And here is our grade for flexure, 0.61. This is fantastic news. A flexure demand capacity ratio of 0.61 means we are demanding only 61% of what this beam can actually handle. We are cruising comfortably under that 1.0 limit. Our beam bends safely without breaking. Finally, Section 4, Checking Final Shear Strength. Remember that hidden battle we talked about? Surviving the bending is only half the fight. We still have to resist the slicing. CalcBook handles shear capacity beautifully because it treats it as a true team effort. The total shear capacity of our beam is the combination of two things working perfectly together. First, the pure structural strength of the concrete itself, which we call VC. Second, the added strength of those #4 steel stirrups we carefully placed every 12 inches along the beam, called VS. Concrete alone is notoriously brittle against slicing. It's the steel stirrups that hold the whole shebang together. So when we combine the strength of our concrete and our steel stirrups against the massive slicing load at that critical 3.49-foot mark, our final shear demand capacity ratio comes out to a victorious 0.42. We are only using 42% of the beam's slicing resistance. This proves beyond a shadow of a doubt that our design easily survives the absolute worst shear zone. We did it! We successfully navigated the internal battle. We used CalcBook and the strict ACI 31819 standards to prove our 24 by 12-inch beam is completely safe, surviving both massive bending and aggressive slicing forces. But I actually want to leave you with a bit of a provocative thought as we wrap up this explainer. With our DCR sitting at just 0.61 for flexure and a super low 0.42 for shear, we clearly have a lot of extra capacity. As an engineer whose job is to optimize, how might you intelligently tweak those concrete dimensions or reduce the steel reinforcement to safely push those numbers closer to 1.0, saving potentially massive amounts of money and material on a large-scale project? It's a really fascinating puzzle to consider. Thank you so much for learning with me today, and keep exploring.